Here we are going to talk about the notion of constant extrema of a function. So let me define this for you. So suppose that D is a subset of R2 and suppose we have two functions f and g. This problem asks us to determine a maximum or minimum of f on D subject to the constant g equal to 0. So let me first remind you of a very familiar example from our high school calculus. We were asked if we were given a rectangle whose perimeter is fixed. So if this is x, this is y, then 2 times x plus y is equal to a. Then what is the maximum possible area of this rectangle? So what is the maximum value of xy that can occur if we are given that 2 times x plus y is equal to a? This is an example of a problem of determining maxima and minima subject to a constraint. So this is the function that we are talking about. We want to determine the maxima subject to the constraint given by 2 times x plus y is equal to a. So let me look at a somewhat more difficult example. So here we are asked to determine what is the maxima or a minima. Remember that we have only talked about local maxima and local minima and not global maxima and global minima. So find the local maximum or local minimum of the function f, which is given by f of xy is equal to x square plus 2y square subject to the constraint gxy is equal to 0, where gxy is given by x square plus y square minus 1. So what is going on geometrically? So suppose that we have so x square plus y square equal to 1, as you know, represents a unit circle. So suppose that this is our unit circle and we have some kind of a coordinate axis. So this is our x-axis, the vertical one is our y-axis, and suppose that the circle is given by the equation x square plus y square minus 1 equal to 0. So geometrically the problem asks us to do the following. So we are supposed to determine the maximum possible value of f of xy, which is given by x square plus 2y square on the perimeter of the circle. This equation is given by x square plus y square minus 1 equal to 0. So in the next couple of slides, I am going to give you a technique which is known as Lagrange's multiplier method, and this will be very helpful in solving this kind of problems. So here is Lagrange's multiplier theorem, and we will also see a couple of examples on how to use this. So what does the theorem say? It says the following. So suppose that D is a subset of R2 and x0, y0 an interior point of D. Suppose we have two functions f and g from D to R that have continuous partial derivatives. So remember, it should have continuous first order partial derivatives in a neighborhood of x0, y0. And suppose that C is the set of all points xy where the second function g vanishes. So in our previous example, it is simply the circle, the unit circle. Now, if the following three conditions happen, or the following three conditions are true, what are the three conditions? G of x0, y0 is equal to 0. So the point in the previous example is a point on the circle, on the unit circle. And suppose that the gradient of x0, y0 is not equal to 0. And the third condition is that f has a local extremum. So extremum means either a local maxima or a local minima at the point x0, y0 when f is restricted to c. In our previous example, when the function f is restricted to the unit circle, then there exists a lambda 0 in R, so a real number lambda 0, such that gradient of f at the point x0, y0 is lambda times, or lambda 0 times gradient of g at the point x0, y0. So these two quantities make sense because not only they exist we have seen that they have f and g have continuous partial derivatives in a neighborhood of x0, y0. So let us just read through the statement. Suppose we have a domain D subset of R2 and x0, y0 an interior point of D, and suppose f and g are two functions that have continuous partial derivatives in a neighborhood of x0, y0. Now suppose we have C to be the set of all x, y in D which vanishes where G vanishes. So suppose we have those three conditions: g of x0, y0 is equal to 0, that is x0, y0 is a point in C. So this is x0, y0 in C. These are equivalent. Gradient of g x0, y0 is not equal to 0, and f has a local extrema at x0, y0 when restricted to C. Then there exists lambda 0 in R, a real number lambda 0, such that gradient of f is lambda 0 times gradient of g at the point x0, y0. This number lambda 0 is called Lagrange multiplier. Lagrange was a very famous French mathematician. He has done lots of things, and as you read higher mathematics, you will see that this name comes up in many subjects in mathematics, many areas in mathematics. So here is how you would use Lagrange multipliers. So first you have to check whether f and g satisfies the condition that are given in the hypothesis of the above theorem, that is Lagrange multiplier theorem. So you introduce a quantity lambda which we call undetermined multiplier. So if you do not want to remember this complicated term, just forget about it. Just introduce a variable, let's say lambda, and then solve for these three variables x, y and lambda in the following system of equations. So we have one condition, gxy is equal to 0, that is our constant. Gradient of f xy is equal to lambda times gradient of gxy, and we have fxxy is equal to lambda times gxxy, fyxy lambda times gyxy, and here we have another equation which is given by gxy equal to 0. So let us do some concrete examples to illustrate this theorem. So the first example is something that we have seen, or that we began our video with. So f of xy is given by x square plus 2y square, and g of xy is given by x square plus y square minus 1. So we are asked to determine what is the maximum or minimum value that f takes on this unit circle. So first we compute fx. So what is fx? Fx is given by 2x. What is gx? So we are going to compute fx at a random point xy. So this is 2x. Gxxy is what again? 2x. Fyxy is equal to 4y, and gyxy is equal to 2y. So I have told you that I need to work with this equation. fxxy is equal to lambda times gxxy, which gives me 2x equal to lambda times 2x. So 2x is equal to lambda times 2x. fxxy is lambda times gxxy. Similarly, this equation fyxy is equal to lambda times gyxy gives me 4y is equal to lambda times 2y. And finally, we have this third equation, which is the constant, which we cannot forget. Now we have this equation to work with, the equation number 1. So it says that 2x equal to 2 lambda x. Now there could be two possibilities, either x equal to 0 or x not equal to 0. So let me divide this problem into two cases. So first I have taken the case when x is not equal to 0. From the first equation, if x is not equal to 0, then the first equation gives me 2x equal to lambda times 2x. X not equal to 0, we can cancel x, and that gives me that lambda is equal to 1. From 2, what do we get? So remember that we are in this case x not equal to 0. From the equation 2, what do we get by putting lambda equal to 1? We get that lambda, so 2y is equal to 4y. So is it possible to have 2y is equal to 4y? Well, this gives me that 2y is equal to 0. So this gives me that 2y is equal to 0, and this in turn gives me y equal to 0. Now if y is equal to 0, I can apply the equation 3, and that will give me x squared to be equal to 1. And what does it mean to have x squared equal to 1? This simply means that either x is equal to plus 1 or x is equal to minus 1. So y equal to 0 and x equal to plus minus 1. These are the 2 points that are given by this condition x not equal to 0. Now what happens if we take x equal to 0? Well, the first equation does not give me anything, because if we put x equal to 0 in both the sides, what we are going to get is 0 equal to 0. So that is fine. But on the other hand, if we look at equation number 3, what do we get is the following. So from equation number 3, we can easily see that y square is equal to 1, and consequently y is equal to plus minus 1, and summing up, we are going to get two additional points which are given by 0, 1 and 0, minus 1. So what are the possible points? By Lagrange's multiplier theorem, the possible points where local maxima and local minima may occur are at the following points, where the points are given by 1, 0, minus 1, 0, 0, 1, 0, minus 1. So first of all, so these are the points, and we have to also check whether these points satisfy, or these points and the functions f and g satisfy all the conditions that were given in the Lagrange multiplier theorem. So I should have g of x0, y0. So suppose that x0, y0, I'll take one of the random points, so 1, 0. So what is g of x0, y0? G of x0, y0 is equal to 0. So 1 square plus 0 square minus 1. This is going to be 0. So what is gradient of f? Gradient of g. So what is gradient of g? So remember that g of xy was given by x square plus y square minus 1. So gradient of g at the point x0, y0, which is exactly given by 1, 0 now, it is given by, so I need to calculate gx at the point 1, 0, gy at the point 1, 0. So what is gx? Gx is equal to 2x. So this is going to be 2. And what is going to be gy? Gy is equal to 2y, and when we evaluate at the point 1, 0, this is going to give me 2, 0. But what we have is that this is not equal to 0, 0. This was the second condition of the Lagrange multiplier theorem. And then we can say, then if f has local maxima or minima, so we have all these conditions that are satisfied, and then all we have to do is that we have to evaluate f at these points. So f of 1, 0 is equal to 1, f of 0, 1 is equal to 2, f of minus 1, 0 is equal to 1, and f of 0, minus 1 is equal to 2. So you can see that among these points, f takes the maximum value 2 at these 2 points. So this is going to be a local maxima. So these 2 points are going to be local maxima, and these 2 points where the function takes value 1 are going to be local minima. So let me work out another example. So here we are to maximize the quantity xy with respect to the constraint g of xy equal to 0. G of xy is given by x square plus y square minus 1. So again, a unit circle, and we have this function xy. So let me proceed in the usual way that we have just mentioned. I will compute what is fxxy. So what is fxxy? This is given by y. Fyxy is x. What is gxxy? This is going to be 2x. What is gyxy? Gyxy is going to be given by 2y. So now fx is equal to lambda times gx. So fx is equal to lambda times gx. So we can write y equal to 2 lambda x. Similarly, x is equal to 2 lambda y. X is equal to 2 lambda y. Now we have the constraint that x square plus y square is equal to 1. So what we do is that we square this whole thing and we square this whole thing and we add them up. So what do this give me is the following: x square plus y square is equal to 4 lambda square x square plus y square. Now we know that this is equal to 1. We know that this is equal to 1, and consequently we have 4 lambda square is equal to 1. And if 4 lambda square is equal to 1, we have lambda is equal to plus minus half. So we have two values for lambda. Lambda is equal to half, lambda is equal to minus half, and let us analyze both the cases rather carefully. So if lambda is equal to half, then what do we have? We had the following. We had seen this before. So let me write down these two equations that we had here already. So we had x equal to 2 times lambda y and y equal to 2 times lambda x. So if lambda is equal to half, then we have x is equal to y. And what was our constant? Our constant was given by x square plus y square equal to 1. Well, so if x square plus y square is equal to 1 and x is equal to y, then what do we have? So we have to use x square plus x square is equal to 1 from the constant equation. So this gives me 2x square is equal to 1, and this gives me x equal to plus minus half. So x is equal to y. So what are the possible points that we are getting from here? So this is 1 by square root 2. So 1 by square root 2, 1 by square root 2. And if x is equal to minus 1 by square root 2, then minus 1 by square root 2 minus 1 by square root 2. So these are the 2 points that are coming from the case when lambda is equal to half. What happens if lambda is equal to minus half? So you can see that this gives me x equal to minus y. So what happens if x is equal to minus y? So the equation will not change too much. So then we are going to again have 2x square is equal to 2x square is equal to 1, and that gives me x equal to plus minus 1 by root 2. So what happens if x equal to 1 by root 2? So then y is equal to minus of x. The corresponding point is minus 1 by square root 2, and if x is equal to minus 1 by square root 2, then we have 1 by square root 2. So now what we need to do is that we have to evaluate if at these 4 points, because these are the points where possibly maxima and minima are occurring. So what is f of 1 by root 2? 1 by root 2. So if xy was equal to xy, so we are just going to multiply these two things. So this is half f of minus 1 by root 2 comma minus 1 by root 2. We are again going to get half. So yeah, remember that the function was xy, so we are not mistaken. So what is f of 1 by root 2 comma minus 1 by root 2? This is going to be equal to minus half, and again f of minus 1 by root 2 1 by root 2, this is going to be equal to minus half as well. So at these 2 points we are going to have a local maxima, and at these 2 points we are going to have our local minima. So let me finish this lecture with the high school calculus example that I had just mentioned. So here we can take x plus y is equal to a. This is our gxy, what is our domain? So not equal to a, so gxy is equal to x plus y minus a. So this is one function, this is our constraint function, this is our constant function. I have f of xy, this is going to be equal to xy. So we are supposed to maximize f of xy with the constraint when x plus y minus a is equal to 0. Well, again I have to do what I have to do. I have to compute fx at the point xy. So this is going to give me y. Fy at the point xy, this is going to give me x. What is gxy? So gxxy is going to be equal to 1. Gyxy is going to be equal to 1 again. And we have another equation which is given by x plus y is equal to a. Okay, so now I have to use Lagrange multiplier. What I get is that y is equal to lambda times 1. So fx is equal to lambda times gx gives me y is equal to lambda times 1. Fy is lambda times gy, this gives me x is equal to lambda times 1. So what in terms that gives me is the following, that simply x is equal to y. So now we have two equations with two unknowns. So x plus y is equal to n and x equal to y. So then this gives me x is equal to half a or a by 2, y is equal to half a. So what is the possible point? The possible point, so I write the possible point because there is only one possibility, x and y are both half a and half a. So the possible point where the local maxima occurs is 1 by 2a, 1 by 2a. And in such a case, what is the local maxima? If it is the local maxima, then the maximum value is given by the maximum value is given by half a times half a, which is a square by 4. So this finishes our discussion on Lagrange's multiplier method.